for what is expected to come. Now these thought experiments also did a pretty good job identifying a lot of different features about these, at least about electricity. One is that there's different types of charges. Another one is that there are different types of materials because they have different relationships with those charges. A few other things are the distance dependency. Right, and some of those are very important. And so we were able to actually garner a lot of information. However, there are still many questions that have yet to be answered. One of those questions is, why are neutral objects attracted by both positive and negative charges? Right, that's a pretty important question. Today we will be covering the answer to that. However, before we begin, before we get to that, we're actually going to go over pretty much all the different elements that were shown here in a very qualitative fashion. We're not going to do anything quantitative this lecture because we're still trying to get a good general understanding of electricity in general. Although for the last 5 minutes we may be able to get through some of the quantitative aspects, but today the primary devotion is to the qualitative stuff. So last class we began talking about charge. We noted that there were two kinds, and we call those kinds just simply positive and negative. And as a reminder, why proton is positive and why proton is positive instead of negative, ultimately just due to convention. There is no fundamental reason why that is. It's just because Ben Franklin said whatever charge proton had was positive, and that's just kind of how it came out to be. Electrons and protons have equal but opposite charges, and that charge is given by this number here. And we left off with just speaking about a neutral object. A neutral object has equal amounts of protons and electrons. And of course, if the number of protons exceed the number of electrons, then the object is, we would say, positively charged. And if the number of protons is less than the number of electrons, then we would say it is negatively charged. And here we will continue. Where's my pen? So large. So the number of electrons can exceed the number of protons when an object gains electrons. So the number of electrons can exceed the number of protons when an object gains electrons. So naturally, objects want to be neutral. Objects want to be neutral. They want to have equal numbers of protons with electrons because of the atom. They want there to be an equal balance so that it's actually it's kind of happy. On the other side, the number of electrons can be less than the number of protons when an object gains protons. Except that's wrong. And here there's an important information that we need to emphasize. Protons do not move. Electrons move. So, how can we ever get to a state where the number of electrons is less than the number of protons? Is if an electron is lost. When an object loses an electron. Protons do not move. Electrons can move. And so whether it be turning into a positive or negative, it's by the addition or the subtraction of an electron. So here, let's just make a note of that. Protons are tightly bound. Its electrons are free to move. Now, understanding that charges come from protons and electrons, we can identify an extension of conservation of mass. So conservation of mass, we can extend this to what the phenomenon called conservation of charge. Now, conservation of mass tells us that mass cannot be created nor destroyed. Well, electrons and protons are considered to be the fundamental sources of mass, meaning electrons and protons cannot be created nor destroyed. So, just like how mass cannot be created nor destroyed, we would understand that charges are also never created nor destroyed. They are merely transferred. Conservation of charge tells us charges are never created nor destroyed. But merely transferred. And that has to do with where the charges come from, and that is the electron and the proton, because they can't be created nor destroyed. Some of those corresponding properties cannot be created nor destroyed either. Now let's do a quick example. I want you to rank in order of charge and use the greater than, less than, or equal to symbol. Is it A? Well, not is it A. Scenario A is simply, we'll call this a proton. B is a single electron. C is an object with 17 protons and 19 electrons. D is an object with 1 million protons and 1 million electrons. And E is a ball missing 3 electrons. Which one has the greatest charge? Which one has the least charge? And we are going to be consistent with a positive and negative notation. Positive is greater than 0, negative is smaller than 0. Any ideas?
Is it E? Is E the most? Has
The
greatest
most?
charge?
Okay, well let's just do it one by one. What charge would A have? Well, it's a single proton, so it would have a charge of positive E. What about an electron? What would the charge of an electron be?
Negative E.
Okay, negative E.
So they're equal.
No. Positive is higher than the negative.
Oh,
Right,
okay.
positive is greater than 0, negative is less than 0. So we're consistent with that. What about object C? What charge will object C have?
-2.
Yeah, it's the net difference that we're looking at. There's 2 more electrons in the number of protons, so the charge is going to be negative 2e. What about D? It would be neutral. Don't let this large number fool you. The overall charge doesn't care about the total number of protons or electrons, just the difference between them. So here, for every proton, there's going to be an electron. They're going to cancel out, so it's going to be overall neutral. If a ball is missing 3 electrons, that means you have an excess of 3 protons. So the charge of E would be positive 3. And so in this case, yes, scenario E, so Q of E is the greatest. Then the scenario that comes next is the proton. Then what comes next is that neutral object in D. Then what comes next is that electron. And then the least is scenario C. That would be the correct answer. Yeah.
When you're dealing with electricity, are we just doing that for this question where -2, like in my head I just think of this charge negatively, it still has like a...
It still has a charge?
Yeah.
Yeah, so if you were to clarify that, then a completely different ranking system would be okay. At which point QE would be greater than QC, which would be greater than QA, which is equal to QB, which would be greater than QD.
Okay. Yep.
Alright, so that was that little discussion on charge. The most important ideas are the fact that there's 2 different kinds, positive and negative. I forgot to mention, opposites attract, likes repel, so opposites attract. Likes repel. So that's Then let's get into the different types of materials that we've introduced in our thought experiments. Those would be insulators versus conductors. To help you guys understand the difference, let's begin by drawing simple sketches of them on the atomic scale. Now, insulators do not like electrons to be flowing through them. And the reason is, if we were to represent insulators with a cube, the atoms, they have a nucleus, but then the electrons would be very tightly bound in the electron orbital. Whereas for conductors, these are the nucleus, so that's the nuclei. Whereas for a conductor, the electrons are not restricted to the electron orbital. A common way that the electrons are characterized for a conducting material is what is called the sea of electrons. So here there is quote unquote a sea of electrons, which of course is trying to emphasize the point that the electrons are just everywhere and they're just freely floating. Whereas in the insulators, the electrons cannot move because they are restricted to just the valence orbitals. So here, electrons are tightly bound. So let's write that into words. So in the insulator, valence electrons are tightly bound. So insulators, if you remember from our thought experiment, the plastic and the glass materials, they are insulating materials. You could still charge them. Insulators are not like charge repellent or anything. They're just charge doesn't move on them. So you can charge insulators. However, when you charge an insulator, because the electrons can't move, wherever it got charged, the electron stays there. So you're going to have patches of staticky areas and patches of non-staticky areas. So charge leads to patches of charge. Patches of charge. Now remember, like charges repel. So the charges kind of want to be as far apart from each other as possible. However, because on an insulator, electrons can't move, they still have to be within close proximity to each other. Yeah.
Sorry, can you please just explain the patches of charge bit again?
So let's say you have a rod, right? Say you have a rod, and then you charge it by rubbing it with wool. Let's say this is plastic. The only part that's going to become charged is where the rubbing actually occurred. And likely it'll just be somewhere over here. Well, let's use electrons in this case, because electrons move. These electrons are not going to want to be next to each other, right? Because like charges want to repel. They want to push each other away. However, insulating materials restrict that kind of motion because the electrons are literally fixed onto like atoms. And so even though they're trying to push them away, well, they kind of have to stay here. They will not spread out to the other side.
And what would happen if it was a conductor?
Yeah, and the conductor, that's what I'm going to be right next.
Okay.
Because you have a sea of electrons, they'll immediately spread out. Immediately spread out. There will not be a buildup of charge. Yeah.
So why is it that the electrons would leave the wool onto the plastic if they don't want to be moving there?
So
Is
that has to do with electronegativity. You're putting two materials. One material really wants electrons. The other material doesn't want electrons. So when you touch it and you apply friction, you're giving opportunities from electrons to jump from the material that doesn't like electrons and then go onto materials that want electrons. Insulators, you can think of it as they want electrons really badly, so they're going to keep it. Each atom is going to keep it. Whichever one has it is not going to let it go. That's why.
Okay.
Yeah. Does that make sense?
Yeah.
So for insulating materials, and you'll actually be able to see this effect tomorrow in lab, because you will be things like you'll be playing with a lot of different things. Conductors, on the other hand, you have the valence electrons, and they are not tightly bound. That is that sea of electrons idea. Therefore, electrons will spread. Now, while we're on this topic of electrons moving, we'll define what is called an electric current, or simply current. This is the motion of charge. Motion of charge. And also, what do we call the objects that actually move? Instead of just calling them charged objects, they're actually given a more proper term called a charge carrier. And so these are charges or charged objects that physically move. So for example, electrons would be a charge carrier. Alternatively, technically you can have positive charges flowing. Protons cannot. However, I'm sure you guys, who's taking chemistry? Raise your hand. Is that everybody? Right, you know of ions. Ions can have a positive charge. These ions can actually physically move. Ions are also considered to be a charge carrier. So charge carriers are not limited to electrons. It's just any entity that is actually charged and moving. Okay, so that's the difference between insulators and conductors. Let's also talk a little bit about charging. We did that in our thought experiments on Monday. You charge different materials differently. So how do you charge an insulator? The answer is rubbing. So that was you applying that frictional force, and essentially the explanation that I just gave Sam. Well, what about conductors? So how to charge conductors, meaning metals. So in this class, whenever we say metal, we're trying to emphasize the conductivity of the material. So how do we charge conductors? You cannot do so by rubbing. Instead, it is through contact. Through contact with a charged object. To demonstrate this, we need to talk about an instrument that is called an electroscope. And this is the object that you guys will be using tomorrow in lab. So let me give you the main parts of an electroscope. You have a metallic sphere, a metallic post, so here metal sphere, metal post. And all the way down at the bottom, you're going to have golden leaves that are going straight down. 2 pieces of golden leaves. And all of this is enclosed in a box that is meant to electrically isolate the inside of the box from everything else. However, for simplicity, when I draw the electroscope, I'm just going to omit this external container that we'll just assume to be there. So how does this work? So using this instrument, you could actually do a lot of these electrostatic experiments, the set of thought experiments that I was discussing on Monday. And this works via the following. Let's say we bring a charged rod to the electroscope, and then we touch it. when we touch it, let's say there's a lot more negative charges. The negative charges are immediately going to go onto the sphere. But what kind of material is the sphere? Well, is pretty much this entire object. What is it?
Metal.
Yeah, it's a metal, meaning it's a conductor. Remember, do negative charges, do they want to be next to each other? And the answer is no. They have like charges repel. They're trying to push everything further away. So the charges are not going to stay on that sphere. Instead, the negative charges are going to be spread throughout the object. Okay, cool. Well, look what happened here. On the golden leaves are now negatively charged. Do you guys see that? One of the things that we discussed in the thought experiments on Monday was that the type of interactions that we get, you do not need contact. Here we have a negatively charged leaf that's very, very, very close to another negatively charged leaf. What kind of interaction do you think they're going to have?
Oh.
They are going to repel, so they're going to fan out like this. So, if you bring a charged object and simply touch the metal sphere, what you're going to see is the leaves fan out. And we see why that process is occurring, because the negative charges are applying an electrostatic repulsion on the leaves. So in the electroscope, what's actually giving you the data is the leaves. This is what you care about. What are the leaves doing? And so here, this is the electrostatic repulsion. Now, what about for positive charges? What do you think will happen if we were to bring a positively charged rod? Well, it's electrons that are moving. So if we bring a positively charged rod, all we're saying is this rod is depleted of some electrons. So when you make contact with the conducting material, the electrons from the metal, or the electroscope, is going to be taken up by our rod. And so what's going to occur is that because electrons are drawn from the electroscope, there's now going to be positive charges that accumulate on the metallic sphere. Once again, like charges repel. Technically, the positive charge doesn't move, but here there's a lot of electrons here that are trying to push each other away. And look, there's now some positive charges here, and so the electrons are going to spread. So what happens is the positive charge also ends up spreading. So the positive charge doesn't remain on the sphere, but also the positive charge kind of spreads out. Technically, we understand that it's the electron moving, but you can still envision it as the positive charges spreading. Now, look at the leaves. They are now both positively charged. Of course, like charges repel, and so you're going to get the same effect, that the leaves are going to spread out, but this time it's due to the leaves being positively charged. So this is the classical electroscope. The one that you're going to be using, unfortunately, they do not have the golden leaves. For the sake of it not getting stolen. Of course, let's just kidding. That's a joke. It's actually because they're super fragile. We actually have one of those traditional ones, but then the gold leaves are destroyed. And if it didn't get thrown out already, I'll show it to you guys tomorrow. The mechanism that your electroscopes will be utilizing tomorrow, you'll just have to wait until tomorrow, but it does work pretty much in the identical fashion. Yeah.
Is it fair to say that the more electronegative a material is, the more of an insulator it is?
I don't think you can say that. I think there is a correlation, but you can't simply look at the electronegativity. Because also things like how large the molecule is does matter. And so just if it constitutes a large amount of space, but you have a very high electronegative substance, but it's also a very large molecule, means the overall electronegative effect is going to be much smaller. So yeah. So I don't think you can say that there's a direct correlation there. Okay, so this is the process of charging, and you're going to be playing around with this in lab tomorrow. But let's briefly discuss the opposite process called discharging. Now let's begin with a discussion about pure water. Pure water. Is pure water a good conductor or a good insulator? Who says it's a good conductor? Raise your hand. Who says it's a good insulator? Raise your hand. Pure water is actually a pretty good insulator. Or at least we'll say it's a bad conductor. It's contrary to what you guys are expecting. Why? Because H2O is not a charge carrier. So H2O, not charge carrier. However, as soon as you dissolve some salts into water, that salt water actually becomes a really, really good conductor because it now has charge carriers. So with dissolved salts, and let's just use the most common one of table salt, NaCl, you'll recognize that it dissociates into Na plus and Cl minus. And look at here, positive charge, negative charge. You have multiple carriers in play. With dissolved salts, water becomes good conductor. Because has charge carriers. Now, humans are roughly 70% water. So what do you think that makes us? Great conductor. So humans, roughly 70%. Yeah, we are 70% salt water. Are good conductors. However, good needs to be in quotes, because we have a layer of skin on the outside, which is a pretty decent insulator. But we have skin therefore, let's just say yeah, good needs to be in quotes because no, actually that's good enough. Which insulates. Now let's do another thought experiment. Oh, yeah, question.
Does water's polarity have any effect on its
Yeah, so
conduction?
that's why it's not like the best insulator. Pretty much everything has this aspect of like polarity. So everything can conduct to some extent, just not well. And that's why rubber is known as the insulator, but if you have enough charge, it will actually conduct the material. So it's a spectrum. So for water, it does have a little bit, but it's not a good conductor, at least on the pure water sense. So let's do another thought experiment. With humans as the test subject. Now, we're not actually going to do it. By that, what I mean is just think about your experience. So humans as test subjects. I'm sure you guys have seen, videos and such of people touching a certain electrical object, and likely a girl's the one doing this, and you see the girl's hair doing what? Right, it poofs up, right? I'm sure most of us have seen a video like this. So, let's say when, or that's the scenario that I'm trying to emulate here. So when touching let's say a charged box, you touch it, our body is not the best conductor. It's kind of a good conductor. Once again, we have this aspect of skin that's around us. Understanding that girls' hairs are going to, go kind of crazy. Why do the girls' hairs go crazy when they touch a, charged object? It's because this charge gets spread out all over us, right? This positive charge goes to the hair, and just like how the golden leaves, they spread out, your hairs are going to spread out because of the electrostatics. So we accrue some of that charge. And this is true even if that mystery box that we touched is a conducting material. We are not as good of a conductor as metals are. However, when we touch it, we still get some of it. Why is that the case? Why is that the case? It's ultimately because we bring a much larger size. So box plus the body is it's not a better conductor, but a larger conductor. Essentially, this idea still prevails even if we are the insulating, or the insulator, acting as the insulator in this scenario. There's a lot of charge that's built up on this conducting object, but we offer a lot of space for the charges to actually spread, and spread it will. So the box plus the body is a larger conductor, therefore we discharge the box. So we are said to have discharged the box. Now let's take this idea one step further. The Earth is also very massive, right? It is very large. I'm sure you guys will all agree with that statement. The Earth is a massive conductor. This is where the idea of, I'm sure you guys have heard of a thing called grounding. This is the idea that grounding is based on. If an object is in electrical contact with the Earth, it is said to be grounded, meaning completely discharged. If we were to touch a charged object, we offer more space, but it is not very massive. So we get some of the charge, but it's still questionable if that charge has been completely depleted. Whereas the Earth, right, the Earth is so massive that we would say, yeah, pretty much took all the charge out. Now, why is that important? Well, for those of you guys that may not have heard of this term before, grounding serves a very important purpose. One thing is so that it won't kill you. Charged objects can kill you very quickly. Depending on the object, if you, let's say, accidentally touch something, it might actually kill you. Microwaves, I don't know if you guys know, are very, very dangerous. So if you ever open up a microwave, you have to be very, very careful. Huh?
Why open it up? What do you mean?
I don't know why you would open it up, but I'm saying if you were to open it up.
You could open it mid-spin while it's still going, or what do you?
No. So even if it's not running, okay.
Inside of a
Inside of it.
microwave.
Yeah, inside of the microwave. Oh,
Like,
We're not
Like,
thinking
not-
about
not
food.
just-
We're not thinking about food.
not just
We're
opening
behind
it to place in the food, but like
okay, so
Yeah, we're not.
actually
We're
unscrew
not-
the back and everything. That's what I meant. I was like.
Alright,
No, microwaves are actually very, very dangerous in terms of their electrical components. And yeah, and accidentally touching some part of it might kill you. And that's why it's, electrical safety is very, very important. And that's the purpose of grounding. It's to make contact with the Earth so any unwanted charge that built up gets fully dissipated and everything now becomes safe to touch again. So the purpose of grounding is to prevent buildup of charges.
Which can.
Yeah.
And so the charge will be essentially conducted to the more massive object, even if it is an insulator?
Yes.
Okay.
Yes. Well, the Earth luckily is not a insulator. It actually has a pretty decent conductivity, but also due to its size, it will still take it in. Yeah.
Okay, so, like how, you mentioned that, like, we human beings, like, we're made of 70% salt water or skin, because of our skin, we also have, like,
Some insulating properties.
yes, insulating properties, so our size is able to sort of offset, or our mass, the fact that we're more massive than, like, a little charged object, kind of offsets that insulating effect.
Yes. Yes.
Okay, alright, that makes sense.
Yes.
Thank you.
Now, the specific relationship is a little bit more complex. Like, that's why wearing rubber gloves will protect you. Because you do have this, you must first get through the rubber gloves before it can actually get to your body. Now, the reason why the charge is able to spread is we do kind of have, these glands. What are glands? All of you guys should know more bio than I do, I think. What are glands?
Guys.
It's anything that produces liquids, right? Like,
Yeah, that's what I was about to say.
like it produces saliva, things like this, the different biological liquids in your body. All of that is water-based, and meaning it also has salt. So all of like your sweat glands are the primary things that would carry it, or why girls' hairs will spread out. Like your sweat glands are taking whatever charge you got on your hands and then transporting it to all the way to everywhere. So technically, the conductivity is important. Yeah, you need some level of conductivity to actually make this effect work.
Okay.
Yeah,
Alright, that makes
yeah.
sense. Thank you.
So grounding is to prevent the buildup of charge so that it won't kill people, so that things are going to be safe. So you don't ever want to touch any electrical component until you know that it is grounded. That's one of the things that safety officers definitely look for in an electrical workstation. That does not mean every single appliance is grounded, like the microwave example. The microwave, how the microwave works, relies on the fact that some components have a really large buildup of charge. And it doesn't get dissipated just because the microwave thing has ended. Right? Okay. So whenever you open up a microwave, not just the door, but like actually open up the electrical circuit and stuff, you have to be very, very cautious. Alright. So that was the process of discharging. With that, we can move on to the following question. Why are neutral objects attracted to both positive and negative charges? We are finally going to answer that question. Hopefully, this was a point of curiosity in our set of thought experiments. Well, we can finally answer that. The answer is what is called charge polarization. So, the overall object although the overall object is neutral, the object can become polarized. And what does this idea of polarized mean? It simply means there can be a slight separation of charge. Slight separation of charge. So for example, let's say we bring a positively charged rod to a neutral object. The overall object, we're going to say, is neutral. Positive charges will attract which kind of charge? Negative. And it will repel what kind of charge? Other positive. In a neutral object, all the negative charges can go into one side, the positive accumulate onto the other side. Because a positive is going to attract the negative, there's going to be a buildup of negative charge on the left. Well, that negative charge must have come from somewhere, and those will be all the way on the right, because the positive is trying to push the positive charges away. Okay, but how's this actually going to lead to a neutral object being attracted to this positively charged rod? Well, remember, one of our thought experiments, we saw that the interaction was distance-based. Was it stronger or weaker as it was closer?
Stronger.
Stronger. Which one? Okay, well, actually before that. The negative charge is going to be attracted to the positive, so there's going to be something pulling. The positive charge is going to be repelling, so there's going to be a force pushing away. But which one is closer? The negative one. So the force with which you are being pulled toward, so we'll say this is the force on the negative. Because this is closer, it is going to be stronger than the force that's being pushed away. So then what is the net force? So actually, let me represent the magnitude with a small arrow. So then what would the net force be? The net force would be an attractive force to the rod. So you would have a net force here. And likewise, we can do the same scenario with the negatively charged rod. If we bring a negatively charged rod to a neutral object, then this time the negative charge is going to attract which charge? The positive. So the positive will accumulate here on the left, whereas the negative will accumulate on the right. And once again, the negative attracts the positive, and the attraction of the positive is closer than the repulsion of the negative. So once again, you still have the net force being toward the rod. This is why a neutral object is attracted to both the positive and the negative, because of this idea called charge polarization. Now, you guys can actually play around with the electroscope that you guys are going to be getting tomorrow, because when you bring let's say a positively charged rod, to a neutral electroscope, what do you think is going to happen to the golden leaves? Will it spread out? Who says it will spread out? Raise your hand. You're not going to touch it though. You're not going to touch it. I forgot to mention that. You just bring it to close proximity of the electroscope. Who says the golden leaves will spread out? Raise your hand. Who says they'll get closer? Raise your hand. Who says nothing will happen? Raise your hand. The leaves will spread because when you bring the positive close to the sphere, the negatives will accumulate here, meaning, well, the negatives, the electrons must have come from somewhere, and the positives are actually going to build up onto the golden leaves. And we have a positive leaf in very close proximity with another positive. So what's going to happen is the leaves flare out. So even without contact, you are going to get a response from the electroscope. Once again, you guys can play around with these tomorrow and observe this behavior.
And why does contact make a difference?
Well, contact, if you were to make a contact, all of this positive is then going to be put onto the electroscope. So if let's say we made contact,
Yeah.
what would happen is this entire thing becomes positive. And then the leaves will spread out. In terms of what happens to the leaves, they're both going to spread. But the reason why the leaves spread are vastly different. One is if you bring it in close proximity, this overall object is still neutral. But the charge polarization makes it so that it will spread. Whereas if you touch it, the overall object is no longer neutral. And that's why it will spread. Does that make sense?
Yeah.
So this leads to what is called the polarization force. And this is not from oppositely charged forces, or charged objects, not from oppositely charged objects, but from charges in neutral object. Well, we'll say charges in object being separated. Now, at this point, there should be a glaring question because of likely an apparent contradiction. In our set of thought experiments on Monday, what was that neutral object that was attracted to both of the rods? You guys remember?
Paper.
Paper! Is that a conductor? Meaning, is that a metal? No, clearly not. Can an insulator do this? Remember, in an insulating object, charges cannot do what? Right, charges cannot move. But what do we show here? Charges moving. This is only for conductors. This is for conductors. So charge polarization happens for conductors. So I kind of cheated, trying to pose this as the explanation for why neutral paper was attracted to both of the rods. What happens to neutral insulators is slightly more complex, and so I'll give you the answer to that now. Essentially, we're building on this concept of charge polarization. For insulators, the actual explanation is, Fatima actually already said it, it is this concept of dipoles. What is an electric dipole? It is essentially charge polarization on atomic scale. So the overall object does not polarize because it can't. The charges cannot move. However, this idea of charges going one place and the other charge going the other place, that can happen on a very much smaller scale. To help you understand what's going on, let's draw a sketch. A neutral atom, we can represent that sphere is the electron cloud or the electron orbital, whatever you want to call it. And you have a nucleus. The nucleus is where the protons belong, or protons are, so that has a positive charge. Electrons are on the electron cloud, so it has a negative charge. But if we were to, let's say, place it in proximity to a positively charged object, of course this is not to scale, what will happen is, what do you think, or actually let me ask you guys a question. What do you think will happen as a result of this positively charged object? Is the nucleus going to be happy being perfectly in the center? And the answer would be no. It's going to be the nucleus. This is a dramatized sketch. Okay, it's not like this pronounced. But what happens is the nucleus favors the opposite side. So there's a shift in the atom itself. So the nucleus kind of gets pushed further away, and the electrons tend to favor this side. So it's not the electrons are jumping from atom to atom, it's whatever that atom is, that just gets distorted slightly. And we will be drawing a few different dipoles. Instead of drawing it in this fashion, we will draw this pill-like structure where the negative is here and the positive is over here. That's kind of how we'll depict it. Likewise, if there's a negatively charged object here, well, this time the nucleus is going to favor the region closer to the negatively charged object. And the electrons are going to kind of favor the opposite side. And to depict this, of course, we will draw the reverse pill scenario. And so why was the neutral pieces of paper, let's say, attracted to our rod? To depict insulating objects, what we would do is break the overall object into its smaller components. And we would try to help visualize this simply by drawing many of these magnetic pills like the following. Now, we're not actually cutting it into 6 pieces. This is simply to demonstrate that on the atomic scale, the negatives are going to favor one side, and the positives are going to favor the other side. And in reality, the actual effect is really, really small. However, these are atoms here. How many atoms are present in the objects that we normally deal with on a regular basis? Many! Many. So that's like, roughly Avogadro's number, which has 23 zeros. So 1, 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 19, 20, 21, 22, 23. That's roughly how many how many atoms constitute the things that we are dealing with. Even though each and every single atom, the effect is really small, there's this many of them. So there is going to be a strong enough effect for it to actually be attracted to the rod itself. So let's say, they win by having a lot of numbers, kind of an idea. And so in all of these, the negative is slightly closer and the positive is slightly further, but once again, there's many of them. So the overall effect, it is actually becomes noticeable. Let's do a simple example. I'm just going to call it an E-scope, right? An electroscope. An E-scope is positively charged. So you bring a negatively charged object close to but not touch E-scope. The question is, what happens? It's a multiple choice question with 3 options. Leaves move further, or we'll say leaves spread out. Leaves come closer, or nothing. So we have a electroscope that is positively charged. And then we bring a negatively charged object close to but not touching the electroscope. What happens to the leaves? Do the leaves spread out? Do they come closer, or nothing? Let's see a show of hands. Who thinks the leaves will spread out? Raise your hand. Who says leaves will come closer? Raise your hand. Okay, who says nothing will happen? Raise your hand.
Wait, it's a positively charged E-scope,
Uh-huh.
negatively charged object.
Uh-huh.
They don't touch.
Yes. But you bring it close enough so that something can happen.
So the electrons want to come towards it. The
What is it?
they want to come towards the E-scope, right? The negative stuff would want to go towards the positive stuff.
Uh-huh.
Yeah, I don't know.
Is it nothing happens?
The answer is they will come closer. Now, why will that happen? Well, let's draw the scenario. Electroscope is positively charged. What does that mean? If an electroscope is charged, what is the starting state of the leaves? Are they straight down?
No, they're not.
No, they're already spread out, right? You needed to get the starting point correct. If it's positively charged, this becomes our starting point. And then when we bring a negatively charged rod close to it but not touch it, the positive charges are going to accumulate where?
At the top.
Right, it's going to be favoring the top. So what's going to happen? The positive charges are pretty much going to rush to the top. But where did these positive charges come from? From the leaves down here. Meaning the leaves end up more neutral, therefore the leaves will get closer. And that is why the answer is B. The leaves will come closer. So you can't just blindly memorize, if X happens with an electroscope, then blank is going to result. No, I can give you a lot of different combinations, and you're really going to have to think things through and process, okay, what is the starting point, how is it being modified, so on and so forth. So that ends the qualitative, a little bit more in-depth introduction to electricity. Now, with the final 10 minutes, let's start going over some of the quantitative aspects, and this is where the main bulk of the electricity portion will begin. So let's call this section 1A, and we will call it electrostatics. Electrostatics. And here we're simply being quantitative about the charge model. to a quantitative approach to charge model. In our set of thought experiments, we covered quite a lot of qualitative features such as distance dependency, opposites attract, likes repel, things like this, but we were not quantitative about how strong the forces were. That requires the quantitative approach in what is termed Coulomb's law. Coulomb's law. Coulomb's law states the following. If two charged particles having charges Q1 and Q2 are lowercase r distance apart, the particles exert forces on each other the following relationship. Force 1 on 2 is actually equal to the force 2 on 1, which is going to equal this relationship. K, some constant K, times the magnitude of Q1 times the magnitude of Q2 all over R squared. And this is a very important equation, and we're going to be utilizing this over and over and over again. However, look at all these vertical lines, right? The absolute value. It gets very tedious and it looks very, I would say, unpleasant. So let's just understand that these Q's have to be positive numbers. Then the equation looks much more palatable, simply KQ1, Q2 over R squared. And this is the form that I'll be using, but it's assumed that Q1 and Q2 are going to be positive numbers. So you definitely want to circle that. I don't think it's very difficult to memorize. However, some of you guys may need to actively drill it into your brain. So Q1 and Q2 are the charges of each particle. R is the distance between them. This K is defined as some people call it the electrostatic constant. Sometimes it is called Coulomb's constant, or some combination of the two, like Coulomb's electrostatic constant. They are all referring to the same thing. And this has a value of 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Newton meter squared per Coulomb squared. Guys, 8.99 is pretty much what? 9. Okay, so let's just use 9 times 10 to the 9th. And that one should be very easy to remember. 9 times 10 to the 9th. That is the value of K. Now, I do have to make you, actually before that. So this only is giving us the force. This is only giving us the magnitude, yeah.
Is it cubed or squared?
Oh, it's squared. Yeah, squared. This only gives us the magnitude. We are missing the what? The direction of the force. Coulomb's law gives us the magnitude, how strong the force is, but it's not giving us any indication of the directionality. For the direction, you already know the answer. It is opposites do what? Attract, like charges repel. That's what it is. So opposites attract. Likes repel. So, let's say we had two different charged objects interacting. To identify the direction, what we would do is find a line segment on which these two particles lie. And so, essentially, you would at least mentally do this exercise of connecting these two particles and then, infinitely extending them. These are both positive, meaning they are going to do what? Repel. So the forces have to be on this line, but they're just pushing each other away. And so if this is Q1 and this is Q2, this would be F21, and this would be F12. Likewise, if both were negative, and you had an improper understanding of electrostatics, you would assume, oh, if positive is pushing them away, then the negatives should be attracting. No, negatives are also like charges, so they are also going to repel. So if this is Q1 and this is Q2, the force is actually going to be identical to the positive cases. This would be F21 and this would be F12. But if one is positive and the other one is negative, then that is how we are going to get this attraction idea, or the forces pointing in the opposite direction of scenarios 1 and 2. So here this would be Q1 and Q2, this would be F21, this would be F12. It's because the charges are opposite in this case. So for the directionality, you always do have to assess the problem that you are given and then ascertain, oh, is it oppositely charged or are they likely charged? That's how you'll be able to get the direction. Now here's the thing. We live in a non-one-dimensional world. So what do you think you're going to have to use to get the direction of the forces? Well, you need to specify things like theta, meaning you're going to need trigonometry. Trigonometry does not go away. Trigonometry will be utilized in this class as well. Now, before we end, I do have to specify one thing. Some people write Coulomb's law as the following. Instead of K Q1 Q2 over R squared, they call it 1 over 4 pi epsilon naught Q1 Q2 over R squared. So these are actually equal, simply meaning K is equal to 1 over 4 pi epsilon naught. You might see this. Some people actually call this Coulomb's law and this fake Coulomb's law, whatever you want to call it. This, some people will argue, is more fundamental. We'll go over the reason why this even came into existence. You might see me use either one of them. Just understand that they're the same thing. This epsilon naught just has a different value of 8.85 times 10 to the negative 12, and it's Coulomb squared per Newton meter squared. Luckily for you guys, you don't have to memorize that because the handbook I'm going to give you, and you will see Coulomb's law constant, right, 8.99, so on and so forth. You also have the epsilon naught, which is called the permittivity constant. That's right here too. And so you'll have access to this, so you actually don't have to memorize those numbers. All right. That's a pretty decent idea, and we'll end it there.